For fatigue calculation, we follow the same fatigue analysis theory. You calculate minimum load on bolt and maximum load on bolt. Initial load will not change. Initial load or preload will always be the same, but the external load is the load that fluctuates from minimum to maximum. So from the fluctuation load, you calculate minimum and maximum load, and then alternating stress and mid-range stress, and then you continue. You choose one of the failure criteria like Goldman line or any other criteria that can also be used. But in bolts, the usually special case with repeated load is very common. Repeated load means joint will be subject to zero external load and maximum external load. Zero external load when there is no external load, and then maximum load. So this is the special case where minimum load is zero. This will give you alternating stress, will reduce your formulas for alternating and mid-range stresses, but the procedure is still the same. Again, you can apply Goldman, Gerber, Liptek, and so on. And always, as usual, stress for check for yielding. In bolts, don't forget to use proof strength from the table, from the previous table in this lecture, instead of yield strength. Okay. Now we move to the other type of joints or connection when bolts are subject to shear, not tension. When bolts are subject to shear, we don't calculate length of threads and grip length and so on. In this case, our design will be based on factors like preventing failure in many cases. So we need to study failure due to these failure possibilities. So in B, this failure is due to bending. So you need to calculate bending stress and make sure that bending stress is less than strength so that bending doesn't happen. Here you calculate shear stress and make sure that shear stress or stress due to shear is less than strength so that no failure in this case. In D, tensile failure of members, you need to calculate stress of the member itself due to this load and this cross-section area, and that must be less than strength of the material of this plate. E, you need to make sure that the area behind the bolt and the member itself will be safe, and also for the bolt material must be strong enough that doesn't crash or no bearing stress will apply to it. The last two, F and G, are the shear tear out and tensile tear out. So first one, as I said, is the bending moment due to bending, and you apply the same formula for bending. You need M, which is a bending moment. So if this is F here, then T is is the grip length, which is the area of everything that's under compression. You need only up to this point, so that is half T. So M will be F T by 2, and then I and C, of course, from the weakest member and this joint. So this sigma must be less than strength of the bolt. Next one is simple direct shear, and this cross section and the cross section of the bolt. Okay, sorry. The next one is tensile failure sigma and the plate itself. So the weakest cross section is this cross section, because we have two holes here. We have two holes, so the area here must be calculated. You need thickness, and you need this length, and you need to subtract the holes. So if we have two holes like this with the diameter D, then you only consider length where there is material. So it's W minus 2D to give you this length, W minus 2D, because we have two holes, times thickness, that gives you the area, this one. And of course sigma must be smaller than strength of this plate. Next is a failure by bearing stress for the material or for the plate here, or for the bolt itself. So we check for both. Okay, so this length is D, and the thickness, the grip length, is T. So area will be dt. This gives you the area, and we use F. Then we can calculate sigma, and we compare this sigma with strength of the plate to make sure that no crushing will happen. For shear out and tear out, we will simply ensure that distance after the space after the last bolt is 1.5 D. So this distance must be 1.5 D to ensure, and this one also, to ensure no shear out or tear out will happen.